All right. So now when we talk about basically this convolutional networks basically produce a feature which can be of any dimension, right? So when you have a convolutional input layer of CHW, it can produce an output of C prime, H prime, W prime. But a lot of the times you require, so C prime, H prime basically depend on the size of the input. But a lot of the times you require a feature that is of fixed length so that you can do some task with it. For example, say retrieval and so on. And so what typically people do is just apply a flat pooling layer. It doesn't matter what the input dimension is. All this pooling layer does is average or take the max across the entire feature map that is produced by the ConvNet. So if the ConvNet produces, say, a 7x7 map, this pooling layer will reduce it to a 1x1 output. If it produces 14x14, it will do the same exact thing. So no matter the size of the input, you'll get a fixed length representation out of this ConvNet. And these global features, the interpretation is that because you're averaging across the entire sort of set of patches contained in the input image, this feature contains something which is global or sort of distinct about this input image, and it describes the entire image just by a single feature. And so here are a bunch of sort of nearest neighbors. So in the sense that you take an input image, you compute its global feature representation, and then you just go retrieve nearest neighbors from an index. And if you look at it, basically, it does turn out that once you do global average pooling on top of these input image features, and you do a nearest neighbor retrieval, it does capture some sort of global sense of the image. And a lot of the retrieved neighbors do have a lot similar semantic concepts as the input image. They may lose some kind of style information. So for example, if you look at the second row where you have a train that's basically facing towards the right-hand side, the retrieved train, the second one, is actually in the completely opposite direction, right? The third one is also in the completely opposite direction. And so now you may wonder why this is happening. Well, if you think about what we did to do this, to like create this image, we did global average pooling, right? And so this global average pooled feature has no sense of spatial structure. We completely destroyed the spatial structure when we were doing this retrieval task. And so of course, when you're doing this retrieval task now, it's not really going to care about the exact pose of the object. The other sort of reason why this happens is typically that we train ConvNets by using data augmentation, and a common data augmentation that is used is horizontal flipping. So the idea is basically that if you flip the image horizontally, the semantic class or the semantic concepts in the image do not change. So this network was likely trained to recognize trains in both poses. So it train to train. Okay. Anyway, so basically you take the input image and then you flip it left to right. And then you're asking it to predict the same exact concept, so bird or whatever, in both versions of the input image. And so naturally, it also reduces the sensitivity of this ConvNet to that particular pose of the input object. And so this brings us to a very interesting point that depending on the particular task that you have at hand, the way that you're training the ConvNet is actually going to matter a lot. If you care about recognizing trains that are facing a particular direction, and then essentially you should stop doing horizontal flipping. If you have a scenario where if you can do actually vertical flipping, and that's actually not changing the semantics of the input image, then that's fine too. But these are things that essentially depend on your application. The way you like for even a simple problem like image classification, paying attention to these types of small details can naturally sort of increase or decrease performance on your task of choice.